Welcome to a demonstration of the production equipment and techniques for design science toys. The Woodmaster planer is a small industrial quality machine with a 12-inch bed, separate 5 and 1.5 horsepower motors for the cutters and drive rollers respectively, and variable speed drive, which is unusual for a planer. Before ripping, all lumber must have a smooth edge perpendicular to its face. We use a completely standard 6-inch grizzly joiner. For ripping, we use a grizzly table saw with a 5 horsepower motor and a 10-inch blade. We've customized it with an extended roller table and a Fox adjustable fence. The fence has various jigs mounted on it that allow us to match the profile of the wood we're using. By ripping at an angle, we were able to significantly reduce our wood waste and produced both tolerances and a cost structure that was superior to a commercial molding company. Here we're ripping wood for our Pura puzzle. At this stage of production, it's a triangular piece that we're producing, so there's no parallel sides. In order to achieve that triangular profile, the board has to be flipped end to end after each cut. It's indexed, and that index mark is used at a later step in production. The small rip saw is a small table saw that's been heavily customized to produce just the small diamond and square profile woods that we use in our puzzle line. In this case, since the wood produced has parallel faces, there's no need to flip the boards end to end. The multi-pass shaper is a 5-horse grizzly shaper that's been heavily customized. We've placed the fences on the outside of the cutter head. The fences are replaceable to match the various angles of the different profiles in production. Tension-loaded roller bearings are used to force the wood up against the fence and keep the tolerances very precise. Rather than standard cutter heads, we use custom machined heads that match the angles of our profiles. The blades are cheap, easy to sharpen, and easy to adjust. The wood profiles are ripped to within 15 thousandths of an inch of their finished dimension. By using the carefully designed production sequence, we're able to always have a finished side against the shaper fence and achieve finish tolerances of plus or minus 5 thousandths on the finished wood. Finished dimensions on the wood are achieved in either 2 or 3 passes, depending on the type of profile being shaped. The entire production sequence for this is well documented. The octet cutoff saw was designed and built in-house. It produces pieces for those puzzles that use octahedral or tetrahedral geometry in our puzzle line. We attempted a couple of larger, more automated versions of this saw, but found the smaller semi-manual design to be more reliable and to have higher throughput. The saw blade is advanced by means of a foot switch. Separate hand controls for controlling the upstream clamp and releasing the stop are immediately in front of the operator. The advancement of the stock through the saw is done by hand. We found human operators to be able to more precisely position the stock against the stop and produce a better toleranced piece than by any automatic means. At a point later in production, the pieces from this stage are fed back in the saw in reverse, producing the opposing angles of the tetrahedron. We've developed various methods over the years of stacking pieces together in a way that amplifies any errors in production. The small diamond cutoff saw is a computer-controlled, automatic, self-feeding saw that produces the small diamond profile used in many of the puzzles in our line. The motor, blade, stop, and clamp assemblies are in the box on the right side of the saw. You can see the feed ramp raising to the left and the solenoids for the air control directly behind. The plexiglass cover that usually protects these parts has been removed for this movie. Profile stock, produced in earlier stages of production, is loaded in the feed ramp and is fed by gravity to the stop and clamp mechanisms. An electric eye senses the presence of the wood and starts the machine in motion. Here, the electric eye is visible as the dark round dot in the background. You can also see the upstream and downstream clamps in action. Automatic feeding of the wood is accomplished through a fairly involved collection of stops, clamps, ejectors, and blowers, all controlled by an industrial computer controller. The controller uses a language similar to the basic programming language and is primarily a series of timing loops that control all of the different air-powered devices. Here we slow things down a bit so you can see the cut, feed, and ejection cycles a little more clearly. Tolerances are checked by assembling the pieces in a pattern very similar to one of our puzzles, in a very carefully chosen reference base. The Roma base saw is used to produce the cradles and bases for many of our puzzles. It consists of a compound miter saw mounted into a fairly complex jig with pneumatic ejectors and clamps. Spring-loaded roller bearings keep the stock positioned tightly against the fence. This view from the side opposite the operator shows the downstream clamp, which prevents the cut piece from falling back into the blade. The dowel machine is our first custom-built machine and one of our most involved. It drills 4 holes and cuts 2 slots, all in the same plane, in 5/16 inch birch dowel that's used in the tensegra toy. This machine has 2 Sagino self-feed drills and 2 custom-built saw assemblies, as well as a host of mechanisms for loading, clamping, and ejecting the piece. Each saw assembly is mounted on its own independent linear slide. A basic stamp industrial controller housed in the small plastic box control these solenoids, which in turn control all of the mechanisms of the machine. Timing loops on the basic controller can easily be adjusted to accommodate for different types of dowel materials, such as plastic. Also visible here are air regulators, water filters, and line oiling devices. In this view, from the operator's side of the machine, we can see the feed ramp and the ejector plate. Each Sagino drill is mounted with 2 drill heads with custom drill bits. In operation, approximately 75 to 100 dowels are mounted in the load ramp. Fins that are usually present on this ramp that allow for additional dowels to be loaded have been removed for visibility. The dowels are gravity fed into V-grooves that are positioned directly below the drills. Dowels are fed from the feed tray into the V-grooves one at a time. As the drills descend, clamps mounted ahead of the drills hold the dowel in place. After the drilling and sawing operations are performed, an ejector plate picks the dowel up from the V-groove and deposits it in a bucket on the exit side of the machine. Blowers, mounted inside each of the clamps, clear dust and debris from the V-groove after each dowel is ejected. The flexible hosing, visible between each of the 2 drills, is also used for dust removal.
Why don't you hit the dust removal?
The machine is mounted on a 1/2-inch thick plate of aluminum. Welded box beams support all of the overhead components. Here we can see the load cylinder in operation. The speed of all cylinders is controlled by flow control valves. This view is from the eject side of the machine, opposite the operator. You can see the operation of the ejector plate, as well as the boxes which surround the saw motor and blade assemblies. Dampeners, mounted on the linear slide assemblies for the saws, help control both the cut depth and speed. This is an industrial controller for the dowel machine. The actual computer is a small chip in the upper left. The rest of the circuitry is for voltage control. One of the more basic pieces of equipment we use is a sander, created by heavily modifying a used washing machine. We pull out the agitator, make a false bottom out of plywood, and line all of the interior surfaces with self-adhesive sandpaper. We found our modified washing machine to be superior to commercial tumblers in producing a nice finish on small pieces. I'm including a slow motion shot here of the agitation just because it looks so beautiful. All of the air-powered machines in our factory were powered by this 180-gallon compressor. It has 2 10-horsepower motors driving twin compression heads. This compressor was able to sustain the simultaneous operation of all of our machines with a 30% duty cycle. The magnet insertion machines insert small cylindrical neodymium magnets into the ends of injected plastic tubes for our Rogers connection toy. Although simple in appearance, these machines have undergone some of the most extensive development work due to the many thousands of operator hours that were logged on them. In operation, the square U-shaped steel fork at the back of the machine is driven forward by a linear slide. The fork slices a magnet off of a stack loaded inside the copper tube mounted behind the cylinder. The fork carries the magnet forward, depositing it on the end of the insertion tool mounted on an air cylinder. Long columns of magnets are loaded into the copper tubes on either side of the machine. Index magnets mounted just behind the central V-block ensure that the polarities are correct. Each tube has a compressional click stop molded into its interior. The air cylinders, mounted on either side of the loaded tube, will insert magnets into the tube. Foot pedals operate both the fork and the insertion cylinders. The compressional click stops hold the magnet inside the tube. Production rates for experienced operators ranged from 1,000 to 1,200 tubes per hour.
Okay, go for it.
A magnet embedded in the end of each insertion tool held the delivered magnet in place up to the point of insertion. The elastic tipping machine was affectionately known as Bucky, named after the two large dies that wrapped and cut the brass around the elastic, which resembled two front teeth. Bucky is a shoelace tipping machine based on a 1940s design that's been modified for use with elastic. The brass tips used on these elastics made the assembly of our tensegratoy product much easier. Here's a view of the back side of the machine opposite of the operator side. The operators pull elastic from continuous rolls on their left, feed it through the large slot in the top of the machine. After the cutting and wrapping operation, they are left with a finished piece of elastic in their right hand. Offset cams in the back of the machine drive the dies forward. A large reel on the underside of the machine feeds a continuous ribbon of brass up to the dies. In production, the operator holds the elastic in their left hand and stretches out to the right. This reduces the diameter of the elastic. After the brass tip is applied, the relaxed elastic expands back into the tip, holding it on even stronger. In this view, you can see where the ribbon of brass feeds up from the bottom into the work area, ready to be applied to the elastic. As the dies move forward, they shear off a small piece of the brass and wrap it around the elastic. In order to see how the elastic is cut, we need to slow the motion of the machine down. The cams that carry the dies forward are offset, causing the right die to move forward further than the left. The result is that both the elastic and the brass are sheared, and a new piece of tipped elastic is created. The brass tips are inserted into small holes on the tensegratoy dowels, eliminating the need for knots. You've been watching a short demonstration of the production equipment and methods for Design Science Toys product line. Thank you for your interest. For any additional information, please contact me at any of the listed addresses.